Today we are going to be talking about negative feedback amplifiers, specifically negative feedback op-amp circuits. So in a negative feedback circuit, let's kind of do what we did the other day with a positive feedback circuit. We start with our open loop amplifier. For a negative feedback circuit, we are going to apply our input signal, calling it x of t as per usual, into a mixer. It gets fed through our open loop amplifier, having a characteristic gain ABOL. Our output is measured at our output terminal. We'll call our output y of t, and some portion of the input signal, the output signal, gets fed back through a feedback network. Having a feedback factor of k, and that portion is then subtracted from the input signal to generate our error signal, E of t, and I'm going to call this guy right here our feedback signal, F of t. So as before, we can see that y of t is equal to our open loop gain times our error signal. Our feedback signal, F of t, is k times our output signal, and our error signal is this time x of t minus f of t. And we can combine all these guys together to get our closed loop gain, AVCL, still defined as our output signal, y of t, divided by our input signal, x of t. But in this case, we get our open loop gain divided by 1 plus our feedback factor times our open loop gain. So negative feedback is very interesting and extraordinarily useful. It wasn't actually invented until I think the 1930s or so by Bell Laboratories, actually. And it is by far the most used configuration in amplifier circuits today. So the application of negative feedback gives us some significant improvements over open loop performance, okay? So some of those improvements include increased linearity or an increased linear range. So we can see that our closed loop gain will always be less than our open loop gain in this type of system. And so when we divide our closed loop gain, which is smaller, by when we divide our supply voltages by our closed loop gain, we're going to get a larger linear range of operation for our amplifier. Another very important improvement of negative feedback is called gain desensitivity. And so what gain desensitivity means is that Like when we looked at the data sheet for the MUA 741 op amp a couple of days ago, it said something about the typical gain being somewhere on the order of 200,000 volts per volt. Now that is typical, but that does not mean that that is the gain of every single amplifier chip produced by Texas Instruments. Probably none of them have a gain of exactly 200,000 volts per volt. Some may be as low as 100,000 volts per volt. Some may be as high as 500,000 volts per volt. So what the gain sensitivity property of negative feedback does is effectively say, it doesn't matter how much the gain fluctuates, the overall closed loop gain of the system is going to be relatively stable. And we'll see that in an example problem that I'm going to work. Another important property of negative feedback is what's called bandwidth extension. And a fourth one, we'll call it manipulation of input and output impedance. We're only going to talk about a couple of these in this class, but we'll talk about all four of these when we get into our analog electronics classes. So let's take a look at specifically a negative feedback op-amp circuit. Bless you, you sneeze so quietly. So we have our amplifier. It is powered because it has to be. We are going to place a resistor, which I'm going to call R2. Between the inverting input terminal and the output terminal. So this is what's giving us some negative feedback. So we had positive feedback when the resistor was placed between the output terminal and the non-inverting input. We have negative feedback when it's placed between the inverting input terminal and the output. We're going to measure our output voltage here. And we are going to place a resistor R1 between our negative input terminal and our input voltage Vn. And in this particular amplifier, we are going to ground our non-inverting input terminal. So I'm going to give us some parameters here. Let's say that R1 is 5 kilo ohms, R2 is 10 kilo ohms, Rn is 1 mega ohm, R out will be 100 ohms, and our open loop gain, AVOL, is equal to 10 to the 5th volts per volt, or 100,000. And our input signal Vn, in this case, I'm going to specify it to be 1 volt. And we are going to want to find several different things, okay? So the first thing I want to find is my output voltage of my system, because this is an amplifier circuit. So finding the output voltage is typically what we've been doing. That's what we've been figuring out, you know, input and output relationships. So to that end, I'm also going to try to figure out a relationship for the closed loop voltage gain, AVCL. I'm going to try to determine what my differential voltage VD is. That's going to be useful. And I'm going to find out what I'm going to call it lowercase rn. So this is the resistance seen by the voltage Vn. And I also want to figure out what my system output resistance is. And this is the resistance seen looking into the output terminal. So we are going to analyze the circuit using first our practical op-amp model. And then from that, we are going to develop some relationships. So with my practical op-amp model, I'm going to start, yeah, that'll work, by drawing my op-amp itself. Here's Rn, which we know to be 100, or it's going to be, I'll just put it as 1 mega ohm, so it makes life easier. Here is the, I'm going to do it with the inverting input terminal on top and the non-inverting input terminal on bottom. And the reason why I'm doing this is going to make it easier to draw the feedback network. Then I have my dependent source, providing me a gain of 10 to the 5th multiplied by VD, where I'm going to go ahead and define VD for you real quick. It's going to be positive polarity on bottom, negative polarity on top right here. So it's always the difference between the, it's the non-inverting input terminal minus the inverting input terminal voltage. So it's got the opposite polarity this time because I changed where the inverting and non-inverting inputs are located. Here's my output resistance of capital R out is 100 ohms. Ground. My output voltage is measured across that open circuit. So since my non-inverting input terminal is connected to ground, I'm just going to short this guy out like so. My inverting input terminal sees a resistance of 5 kilo ohms. And then my signal voltage or my input voltage of 1 volt. And I also have feedback being applied from my inverting input terminal to my output terminal. So that's this resistor here having a value of 10 kilo ohms. In order to develop a relationship to figure out what V out is, I'm going to have to apply Kirchhoff's current law. I'm going to apply it at the inverting input node. So I'm going to sum these 3 currents together. And then I'm also going to do it at the output node, where I sum these 2 currents together. So when we do KCL at the inverting input, what I get is V minus 1 volt divided by 5 kilo ohms. My current to the right is V minus minus V plus, which is 0. So V minus over 1 mega ohm. And lastly, my current up is V minus minus the out divided by 10 kiloohms is equal to 0. So that's one equation. When I perform KCL at my output node, the current directed to the right is V out minus 10 to the 5 times VD. All right, but VD can be expressed in terms of V plus and V minus, right? So since VD is always V plus minus V minus, and V plus is 0 volts, VD is just negative V minus. Divide this guy by 100 ohms. And now I have my current flowing through my feedback loop. So that's going to be V out minus V minus divided by 10 kiloohms is equal to 0. So I have two equations and two unknowns, right? So I don't know what V minus is and I don't know what V out is. If I solve these guys simultaneously, what I find is that V out is negative 1.9999392 volts. And I find that V minus is 20.199 microvolts. So my answer to part A, this guy, right? I figured out what the voltage is. It's something extraordinarily close to -2. So really the only thing to say here, a couple of interesting points, I guess. The first of which is this is the first circuit that we've dealt with where the output voltage isn't VCC plus or VCC minus, right? Now we technically haven't specified VCC plus or VCC minus. I guess I should have done that, but it's not going to show up anywhere in the calculations here. But if VCC plus and VCC minus have a larger magnitude than this plus or minus 2 volts we're seeing here for the output, then we should see that our output signal is actually at this particular value, not VCC plus, not VCC minus. We have a negative output signal caused by a positive input voltage. That is because we are applying the input signal through our feedback network to the inverting terminal. So if we had done a similar problem, except we'd applied the input signal to the non-inverting input terminal, we would actually see that we would get a positive output signal. So that's really all we can say that's interesting right now about V out. V minus is 20.199 microvolts, which means in turn, our differential voltage, VD, is negative 20.199 microvolts, right? So this is interesting in as much as we're applying 1 volt through a resistor network to one input, 0 volts to the other input terminal, and we're seeing that there's only a potential difference of 20.2 microvolts between the actual input terminals. This is an interesting revelation, and we'll talk about exactly why this happened shortly. This is the answer to part C of our question. For our closed loop voltage gain, AVCL is going to be our output voltage, negative 1.99999392 volts, divided by our input voltage of 1 volt, gives us a gain of negative 1.9999392 volts per volt, which is the answer to part B. So this is very interesting. We had an open loop gain of 100,000. And because of our resistor network, the magnitude of our gain has reduced to 2. So going from 100,000 to 2, roughly, is fairly significant. Now, if we were talking about that gain desensitivity thing earlier, if we increased the magnitude of our open loop gain to say 10 to the 7, so 10 million or something like that, we would actually still get a gain really, really close to 2. If we lowered our open loop gain down to 1,000, we would still get a gain really, really close to 2. This is what gain desensitivity is all about. So we can have a lot of play in the open loop gain and still get a very specific closed loop gain with only a very small amount of error on either side of it, okay? So let's look at our input resistance. And let's talk about how we might go about calculating it. That's something pretty important as well, okay? I'm going to do it in orange. So our lowercase r input resistance is the resistance seen by our voltage source. So another way to think about that is I'm going to call this lowercase I in, and simply the current that's leaving that voltage source, or the voltage drop over the voltage source divided by the current leaving the voltage source gives us the resistance connected to the voltage source. So what I'm arguing is that if we have a voltage source Vn connected to a black box network that we're trying to figure out the resistance of, I can figure out the voltage drop across the input terminals of the network, which I know because I specified it as 1 volt, and the current flowing into the input terminal of the network. The input resistance of our system, as seen by our voltage source, is simply Vn over In, just Ohm's law, right? This is literally how Ohm's law is defined, or at least it is when I teach it in Circuits 1. So we know what our input voltage is. It is 1 volt. How are we going to find that input current? Any thoughts?
It would have to be the difference between V minus and V out over the 10 kilo ohm, because there wouldn't really be any going, or any current going through the 1 mega ohm resistor.
I agree with part of what you said. So IN is the current flowing out of the positive polarity terminal of our 1 volt source, right? So it's the current flowing through that 5 kilo ohm resistor from left to right. So why don't we just use Ohm's law over the 5 kilo ohm resistor? We know the voltage on both sides of it. We know the resistor value. So that gives us the current, right? So that would be 1 volt minus 20.199 microvolts divided by 5 kiloohms is going to give us something really close to 5 kiloohms. 5,000.100997 ohms. So effectively, that should be D. The input resistance of this particular system is governed by that resistor that we put between the input voltage and the input terminal, okay? Now, if this were instead where we applied the input voltage at the non-inverting terminal, so if we had applied the input voltage here, we would actually see something pretty interesting. Our input resistance of 1 mega ohm would actually be amplified by a significant amount. Like we would expect it to look like something potentially on the order of as large as tera ohms. And that is because of the way that negative feedback has an opportunity to change the input and output resistance depending on the way the feedback network is connected. So really what we have here is we have this small, with this particular configuration, that resistor R1 is connected in parallel to that astronomically large internal input resistance of the negative feedback op amp, which makes it look like pretty much just that one resistor. When we change where we're putting ground in our input signal, we don't have that resistor there in parallel anymore, and so it just looks like that huge, huge resistance. And you're going to work a homework problem with exactly that. So I'm telling you this, don't be freaked out when your answer for the homework problem is your resistance is something like 5 times 10 to the 10 ohms. It's going to be enormous. It's correct. For our output resistance, we are trying to figure out what resistance we see looking in through the output terminals, okay? We have a pretty gnarly looking network right here, right? And we, in my opinion, would be kind of hard pressed to figure out, I guess technically we could turn our voltage source off, our 1 volt source off, and apply a test source and see what happens. But I don't want to do that. The reason that I don't want to do that is because I'm going to use effectively the Thevenin and Norton equivalent circuits to figure out the resistance seen by that open circuit set of terminals, right? And the reason why I'm going to use Thevenin and Norton is because we already know what the open circuit voltage is. So now I just need to know what the short circuit current, and once I have those 2 pieces of information, I know what my output resistance is, right? So I am, to clarify, I am saying that R out is going to be V Thevenin, which is V open circuit, which is exactly the same as the V out we've already calculated because we measured the open circuit voltage, divided by I Norton, which is the short circuit current, right? So I'm going to come up here and I'm going to modify this guy very slightly, and I'll do it in this pink, I guess. So here's where our Norton current is going to flow, right? So how does this change my analysis that I did previously? Something pretty important here.
It shorts the R out. And
So I wouldn't say that it doesn't short out uppercase R out the 100 ohm resistor, because that short circuit isn't in parallel with the 100 ohm resistor, but it does short out the output voltage. So the output voltage is going to be fixed at 0 volts for this system, right? So if we look at our KCL at our inverting input equation, where we know that V out is exactly equal to 0, that lets us solve for V minus and therefore VD, which gives us enough information to figure out what that current is. And so what I mean by that specifically, this current plus this current together, using Kirchhoff's current law, add together to form I Norton, right? The pink current on top, if I know what that voltage V minus is, I have all the information I need, because it's just going to be V minus divided by 10 kilo ohms. And the pink current on the bottom is just going to be 10 to the 5 times minus V minus divided by 100 ohms. I add those two guys together and I get my Norton current. Does that make sense? So I'll write it down in pink here. So if we do ACL at our inverting input, we find that we have V minus minus 1 volt divided by R1, which is 5 kilo ohms, plus V minus over 1 mega ohm, plus V minus over 10 kilo ohms is equal to 0, giving us V minus is equal to, where do I have it written down? There we go. 0.66445 volts. I Norton, using Kirchhoff's current law, is equal to V minus over 10 kilo ohms plus 10 to the 5 times negative V minus over 100 ohms gives us negative 664.45176 amperes. And so finally, I can say that my output resistance, seen looking into the output terminals, is again V Thevenin over I Norton. So that's negative 1.9999392 volts divided by negative 664.45176 amps gives me an output resistance of 3.0085 milliohms. So our output resistance here goes from, or the output resistance of the op amp was 100 ohms, but the output resistance of the system, including negative feedback, is 3 milliohms. So we saw a significant reduction in output resistance. That's going to happen anytime we actually wind up measuring a voltage with a negative feedback system. So we just covered a lot of stuff. How difficult was that circuit analysis? Not particularly difficult per se, but definitely a bit tedious, right? So let's circle back around to one of the topics that we talked about at the very, very beginning of this class, all right? And that is of an ideal amplifier. So we have learned that any amplifier can be characterized by three parameters: the open loop gain, the input resistance, and the output resistance. At the beginning of class, we had our amplifier and we had it connected to a practical voltage source. So this was Vs of t, and then this voltage drop here, Vn of t, served as the input voltage to our amplifier circuit. This voltage was the output voltage of our amplifier circuit, and we had the output connected to some load resistance RL. This was VL of t. And we said that ideally, our load resistance VL of t was just going to be some scaled version of our input voltage Vs of t. This is one of the very first things we talked about when we started getting into lectures in this class. So my question to you guys is, what value of our parameters, R in, R out, and AVOL, make this happen? Okay. Two of them are going to be easy. Another one is going to require a little bit of explanation. All right. So we're going to break this down into a couple of simple steps. If I want, or so let's say, how do I make Vn of t exactly equal Vs of t? What value must Rn have to make those two voltages identical? So if Rn were 0, then Vn would be 0, which is not necessarily Vs of t. So think about it the other way around, right? If Rn were infinitely large, so an open circuit, no current could flow in the input loop, which means there would be no voltage drop over the resistor Rs. So Vs and Vn would be identical. Does that make sense? Let Rn equal to infinity. All right. How do I make AVOL times Vn of t exactly equal V out? So what value of R out forces those quantities to be identical? 0. So in an ideal case, our input resistance is infinitely large and our output resistance is infinitely small. And we've seen that negative feedback forces our output resistance to be pretty dang close to 0. And I need to change the example problem for later on. If we had done a non-inverting amplifier, we would have seen that our input resistance is getting closer and closer to infinity as well. So we also need to figure out what value of our open loop gain would be the ideal case. And so that's going to come back around to our closed loop gain expression that we developed earlier, right? So our closed loop gain expression, AVCL, was equal to our open loop gain, AVOL, divided by 1 plus K times AVOL, right? Before I explain what's going on here, I want us to take another quick look at this problem that we had. Okay. Our gain here of -2, effectively, we're very, very close to -2, was not in any way, shape, or form by coincidence. All right. Our gain was established by our feedback resistors, the 10 kilo ohm resistor and the 5 kilo ohm resistor. The negative sign came from the fact that we applied our input signal to the inverting input, but the magnitude of our gain came from our feedback network. So if I want my closed loop gain to be dependent only on K, which is my feedback factor established by my feedback network, what value does AVOL have to have? It's not going to be 1. All right, so let's say if AVOL is 0, my closed loop gain is always 0, right? That's obviously not what I want. So let's go to the opposite end of the spectrum. If my open loop gain is infinitely large, this becomes infinity over 1 plus K times infinity, which is approximately 1 over K. So my gain, my closed loop gain, is entirely determined by my feedback loop when the open loop gain is infinitely large. So our third condition for an ideal op amp is that AVOL is infinity volts per volt. So we are going to revisit that problem using our ideal op amp parameters. All right, so the exact same problem. Here's our feedback resistor, R2. Here's R1. This guy was grounded. Here's V out. R1 was 5 kilo ohms. R2 was 10 kilo ohms. In is infinitely large. R out is 0 ohms. AVOL is infinitely large, and the in is 1 volt. Our goal here is to just find the closed loop gain of the system. All right, which we'll get by determining the output voltage and dividing it by 1 volt. So if I were to draw my practical op amp model representation of this guy, treat this guy as infinitely large. Here's V plus, here's V minus. This is infinity times VD. This guy looks like 0 ohms. Here's my output voltage again, V out. short this guy. 5 kilo ohm resistor goes here. 1 volt goes here. Kilo ohm resistor goes here. All right, so before we get to applying Kirchhoff's current law and all that kind of good stuff, which we are going to have to do, I wanna look at something real quick here. All right. V out is equal to infinity times VD. By definition, it can't be literally anything else, correct? Well, if I rearrange this guy, VD is equal to V out divided by infinity. Which is 0 volts. Has to be. What does this imply? VD is equal to V plus minus V minus is equal to 0 volts. Or this is how we get our voltage constraint equation, or one of our ideal op-amp rules. V plus has to be exactly equal to V minus in an ideal op-amp. So now let's take care of that KCL equation. We're going to have this current, and this current. Well, KCL at our inverting input, we're going to have V minus, which we actually know to be 0, since V plus is 0, minus 1 volt. So we have minus 1 volt divided by 5 kilo ohms plus the blue line directed, or the blue arrow directed to the right through our infinity ohm input resistance gives us our other ideal op-amp rule. No current can flow into or out of the input terminals because it's an infinitely large resistance. So we're going to have to just do the top path there. So that is going to be V minus, which is 0, minus V out. So negative V out over 10 kilo ohms is equal to 0. Solving this gives us V out is equal to 2 volts. And from this, then, our closed loop gain, AVCL, negative 2 volts per volt. So this analysis using the ideal parameters, I feel was a little bit easier than the last problem, at least less tedious, but we can specify specific ideal op-amp rules and never have to use the practical op-amp model again for any negative feedback op-amp circuit, right? So the ideal op-amp rules that we have developed here are only valid for negative feedback circuits. So the first rule comes from our voltage constraint equation. There can be no difference in potential or voltage between the input terminals other words, V plus is equal to V minus. And our second rule is no current can flow into or out of the input terminals. So if we revisit this problem a third time, and I know we're beating it to death, we can apply these op-amp rules and no longer have to use practical model, which takes time and effort. Guy was our 10 kilo ohm resistor. Here we had our 5 kilo ohm resistor, ground, and 1 volt. So if we apply our first rule, this voltage, V plus, is equal to 0 volts by inspection, which means this voltage, V minus, is also equal to 0 volts. This current, I'm going to call it I plus, is equal to 0 amps. And this current, I minus, is equal to 0 amps. So we can easily say then that this current, I'm going to call it I, is the same as this current I flowing through our feedback resistor. And I can say then that, bless you, I is equal to 1 volt over 5 kilo ohms. I is also equal to negative V out over 10 kilo ohms. And if I set these guys equal to each other, I get the exact equation I derived previously. Negative V out over 10 kilo ohms is equal to 1 volt over 5 kilo ohms, giving us V out is equal to negative 2 volts. And AVCL is negative 2. Much less math, drawing schematics, all that kind of jazz. All right, so I think that is enough out of me for today. On Tuesday, we will apply these two negative feedback op-amp rules and develop a methodology for solving any and every negative feedback op-amp circuit. And then we will also introduce commonly used negative feedback amplifier topologies and talk a bit about their applications and all that kind of good stuff. So any questions?
Did we apply these ideal rules with all op-amps that we worked on in circuits?
Yes. The ideal op-amp rules were used on every single circuit that you dealt with in circuits 1, and it's because in circuits 1, every single op-amp circuit that you dealt with was a negative feedback circuit. You didn't probably realize it because it wasn't pointed out to you, but if you go back through and look through your notes, the homework problems and all that kind of stuff, every single one of them has a resistor or a wire, that's also valid, but a connection made between the output terminal and the non-inverting, or excuse me, the output terminal and the inverting input terminal. If that's the case, ideal op-amp rules apply the overwhelming majority of the time. And by that, I mean like 99.999%. The only reason they wouldn't apply is if you had an extraordinarily poorly designed op amp such that the open loop gain were only like probably less than 100 might start breaking things. But most practical op amps have open loop gains of at least 1,000. So all this still works.
So an op amp amplifies voltage, right?
Yes.
So when you take the output voltage and put it back in amplifier.
So you're not necessarily forgetting, but you're not fully understanding the behavior of the mixer. And so it's because this is a differential system or a differential amplifier at its heart, okay? So an op amp amplifies the difference in the voltages. We are forcing those differences in voltages to be effectively zero, yeah. And it's because one terminal adds a voltage, that's the non-inverting terminal, and the other terminal subtracts a voltage, that's the inverting terminal. So that's why in positive feedback, we were adding some of the output to the input. So we forced it to saturate faster than if it were an open loop system. Yeah, it's always going to oscillate between VCC plus and VCC minus. When we apply negative feedback, we're actually constraining the gain to effectively being entirely dependent on the biasing network. So we have very, very, very good gain stability at the expense of having a very, very, very small gain in comparison to the open loop gain. Not saying that a negative feedback op amp can't be used with extremely high gain. Like that's how a lot of guitar effects pedals work. Is an op amp, a negative feedback op amp with very, very high gain. And what the high gain does is typically the gain is set with a potentiometer. And so when it's set to be a very low gain, the output signal is exactly a scaled version of the input signal. It's just louder, effectively. But as you turn the gain up, then you hit saturation distortion. Effectively, it's clipping things off, and that's making the sound more interesting. And the higher you boost that gain, the more it gets closer and closer to looking like a square wave, effectively. That's typically the input stage of most guitar distortion pedals. The output stage might also have some diodes to do some other type of clipping, so you can set up asymmetrical clipping or make it harsher or not, just depending on whether you're using like specific diodes, or you can either do it with LEDs. Actually, some pedals use LEDs inside now for their clipping stages. And if you use two different color LEDs, you get asymmetrical clipping because they have different current voltage characteristics. So we are going to talk about cascading amplifiers on Thursday. So I will wait until then to answer that question because I already have it on the books. Any other questions? Alrighty, I will see you guys bright and early tomorrow morning. Thank you.